Hello everyone, welcome to Module 3, Part 1. So this is our first part of Module 3, and Module 3 is going to focus on Chapter 4 in our textbook, which is on energy analysis of closed systems. So we're going to continue analyzing and looking at closed system just like we did in the previous module, and we're going to start our analysis on moving boundary work. Now, this module also uses parts of Chapter 2, which will be talked about throughout this chapter and combined with Chapter 4 as well. So the first thing we're going to talk about is moving boundary work and defining what moving boundary work is. And the first diagram that we're going to draw, which we usually always start with in our thermodynamic analysis of closed systems, is our piston cylinder device. So let's look at a piston cylinder device. So we're going to have a piston inside a cylinder. I'm going to put a handle on that piston so we can see what's happening. And we're going to say that we have a gas within this piston cylinder assembly. And moving boundary work can be defined as a form of mechanical work frequently encountered in practice and is associated with the expansion or compression of a gas in a piston cylinder arrangement. So it defines expansion or compression of a gas in the piston cylinder arrangement. So I'm going to write down the definition so everybody has it, but it is a form of mechanical work frequently encountered in practice. So we see this in a lot of different situations. And that is associated to expansion or compression of a gas in a piston cylinder assembly. And I really want to take some time to understand what's happening here, and having the definition here I think is important. Okay, it's also sometimes called, moving boundary work is also sometimes called PDV work. And how we can define this work is essentially we have a system boundary, which is shown right here. So this is our system boundary. So remember, when we make these dotted lines are usually the boundary of our system. The system is inside this boundary, and then outside this boundary would be the surroundings. So anything outside would be called the surroundings. Okay, in our convention that we discussed earlier on in the class. And the PDV work is associated with the movement of this system boundary. So this system boundary can move. Okay, if we have a piston cylinder assembly, we know that this boundary can move up or down. So this piston can move up or down. The movement up or down is what creates this moving boundary work. Okay, so this is the moving boundary work. And we're going to define the equations that go with it as well, but this is just an explanation. So if we have a piston cylinder assembly and we decide, for example, to increase the temperature of a gas inside it, usually the gas is going to expand and the piston would move up. Okay, that would be an example. Now, in our in our class, we're going to be focusing on, as we had said earlier, we're going to be focusing on quasi-equilibrium analysis. And what that means is that the system remains nearly in equilibrium at all times. So we can stop the system at any point and we can assume that the system would be in equilibrium. This is okay in slow systems. Okay, this is okay in systems that move slowly. Once the systems move very, very fast, it might be a little bit harder to capture actual values that would happen in real life. So we're going to say that the system remains nearly in equilibrium at all times. Okay, so we're going to be focusing on these types of systems. We're not going to be looking at highly transient systems that move very fast. Now, according to convention, and this is just how we define it, we're going to say that when the gas expands, so let's say we heated a gas and then the gas starts expanding, we're going to say that work is positive. So this moving boundary work is now positive. Okay, it's a positive work. And what that means is if we define our gas as the system, so this part is the system, if we define the gas as a system and the system is expanding, we're going to say that since the work is positive, we're going to say that work is done by the system. Okay, the work is done by the system onto the surroundings. We're moving the piston up towards the surroundings. Okay, so the work is done by the system. Now, when a gas compresses, we have the opposite. So when the gas compresses, by convention, work is negative. And what that means is that the work being done is now on the system. So work done on the system. Okay, so the surroundings is essentially compressing the system in some way. So the gas is compressing, therefore the work has to be done from the outside to the system itself. Now, if you can think of different systems where this can be applied, it can be applied to, for example, internal combustion engines. So if you have an internal combustion engine, you have a piston that moves a crankshaft and the piston moves up and down, and so the work is positive, then negative, then positive, then negative, and the piston keeps moving up and down. Okay, so if we look at our diagram again, just to summarize what we wrote right above, if we have a piston cylinder assembly, we have our system delimited by our boundary. So this is our system. And anytime our piston moves up, we have positive work. And anytime our system moves down, or our piston moves down, sorry, we have negative work. Okay, so that should help in understanding what's happening. So you can essentially always know, if you know that the piston's going up, you know the work is positive. Okay, if you know the piston's going down, the work is negative. So now let's consider a system with a gas. So let's consider a system with a gas in it. And the system is again contained in a piston cylinder device. So I'm going to use CYL for cylinder throughout the lectures, so just to let you know. Okay, and this piston looks something like this. So in the same ways as before, it just looks like this. And once again, we have our gas trapped inside and our system is inside. Now, what we're going to add to this system is we're going to add some weights. We're going to add some weights on top of our piston. So this is the piston, and we're going to add some weights on top. Now, what happens if you start removing weights? What happens if you remove the weights? If you remove the weights, you're essentially lowering the force acting on the piston. And if you lower the force acting on the piston, that means that the pressure is going to go down. So what's going to happen to our pressure? If the pressure on the system goes down, what's going to happen is our piston is going to move up to a new position. Our piston, if we take off all the weights, is going to move up to a new position. And we're going to define this distance, this change in distance, as ds. Okay, so we're just going to call it, it goes up by ds. And we also know that the piston has a cross-sectional area A. Okay, and we're also told that it has an initial pressure P. So the system has an initial pressure called P. Okay, and we're defining these values so that we can come up with a derivation and an equation for the system. So the work, and since this is a differential distance, okay, we're looking at a ds, the work is going to be equal to dWb. Okay, and it's given, the work is given by, and you should know this from other classes, that work is equal to force times distance. So d work of the boundary, so this little b means boundary. It's called the boundary work, okay? So we use a little sub b to make sure that we understand that we're talking about the boundary. And this work boundary is equal to F times ds. So it's the force on the system multiplied by the change in distance. And we also know that the force is equal to the pressure times the area. Okay, that's the definition of force. Therefore, we can write that our differential work, or our work, is equal to PA times ds. And what is this term equivalent to? It's the area times the distance. ADS is equal to dV. It's equal to the change in volume of the gas. So this is equal to the change in volume of the gas. And you don't really need to know all this derivation, but it does help you explain how we come up with the equation for work and what equation we're going to be using for work throughout this class. So we can rearrange this ADS is equal to dV. We can say that ds is equal to dV over A. And so if we say that ds is equal to dV over A, we can actually write from this equation, we substitute for ds, we can write that dWb is equal to pressure times area over dV over area. And now we can cancel out the two areas. So we're left with dWb is equal to P dV. And that's why it's called the P dV work. Okay? It's the differential boundary work. This is the differential boundary work. So this is called the differential boundary work. And this equation is in terms right now of dW and dV. Okay, it's a differential right now. It's not an explicit form. Now, if we integrate between 2 points, if we integrate between two different points in our system, so for example, if this was 0.1 and this was 0.2 for our piston in terms of distance, we could integrate between 1 and 2. So we could integrate and say that the integral from 1 to 2 of work boundary is equal to, d work boundary, right? We have integral of 1 to 2 d work boundary is equal to the integral of 1 to 2 p dV. And we can say that this is equal to the total work from one point to another, which we're going to just call WB, right? If we integrate dWB between 1 and 2, we just get work boundary from 1 to 2, okay? Now, this integral from 1 to 2 of PdV, how do we solve this side of the equation? How do we solve it? Okay, we have pressure and dV. So what are the ways we can solve this? There's two ways we can really solve it. One is to solve it visually, and this visually is that if you remember correctly, the integral is just the area under a curve. So if the curve is very simple to analyze, let's say it's a flat line, it would be very easy to find the area under a curve. So one way to do it is to find the area under a curve. Okay, so very simple way. Now, number two is we would have to solve it in a different way. How else can we solve this equation? We need to solve it if we have an equation for pressure in terms of volume. So if pressure is equal to a function of volume, then we could solve it. Okay, we need our pressure term to become somewhat of a volume term so that we can solve VdV with its system. We can also solve it if pressure is constant, right? If pressure is constant, we just go outside the bracket and then it's just P multiplied by the change in volume. Okay, so if the pressure is constant, we could also solve it very simply by just by integrating just 1 to 2 of dV and taking P out of the bracket, but that's another method. So this would be solved, if P is a function of V, it would be solved mathematically. So we would be able to solve it mathematically. If not, we have to use the area under the curve. Okay, so let's try and see what that would look like on a graph of PV. So if we have a PV diagram, okay, these are called PV diagrams or PV graph, and you would have 0 here at the bottom left. You could have a system going from high pressure and low volume, which would be the case in our system above. Okay, in our system with the gas, we're going from a low volume to a high volume, and from a high pressure, because we have a high pressure due to the weights, to a lower pressure because the weights are taken off. So we have some sort of curve that looks like this. We go from 1 to 2. Okay, and from 1 to 2, this is our process. Okay, our process is from 1 to 2. We have to, so this is called, just to write it out because we haven't done this in a little bit, it's called the process path. Okay, it's the process path from 1 to 2. Now, we can also label on the graph that we have V1 here, volume 1, and we have a certain volume 2. So how are we going to solve this problem? Now, one way to look at this too is we can actually put our piston cylinder assembly laying under the graph, and we can show our piston at volume 1 initially with the gas in here. Okay, so we're laying it sideways, and then the piston would move up to this new level right here. Okay, due to the fact that we took out the weights. Okay, so that's just a visual of what's happening. Now, if we show the process on a PV diagram, how are we going to solve for the work? Well, the work is going to be an inexact differential. It's going to be a differential. So what we're going to have to do is find the total area. So we're going to have to find the total area under the curve. So finding the total area under the curve, we can say that this total area under this curve is going to be equal to WB. And if we zoom in a little bit and we actually look at the system itself, we can write that the system is essentially a sum of little differential volumes, right? If we look at it from a calculus point of view and figuring out how to find the volume, we can actually use very simple little slices, okay, little slices that you would add up all together in order to get the integral. So that's how you would do it. And this area of the system here, dA, would be equal to P dV. Okay? And so it means that the total area, just to rewrite it, would be equal to A. Okay, we can call this area A. So this area in green would be equal to A, is equal to the integral from 1 to 2 of dA, okay, all the differential area. And this is equal to the integral of P dV. So this is just to show you how the volume, how the area under the curve is equal to the total work boundary. Okay, so moving forward from this, so the total area is obtained by adding all the differential areas, and the area under the curve is just the sum of all these areas, essentially. Okay? So in the case of a compression process, if we have a compression process, our process would look something like this. So if we had a compression in our system, so now we have, let's say we have, if we lay our piston cylinder sideways on the graph and we have a compression this way from point 1 to point 2, our graph would now look something like this. We have 1 to 2, and our path is now going towards the left. So anytime something on a PV diagram is going towards the left, you know you have a compression. Anytime something is going towards the right, you usually have an expansion. Okay, that's a good rule to remember. Now, what if we look at different paths that the system could take. So let's say that we have pressure versus volume, and now we have point 1. How do we know the shape that the path is going to take? We don't really know the shape, right? The area could be different depending on the path. So from 1 to 2, we could have taken a path A, sort of like we showed before, or we could have taken a path B, which would lead us straight from 1 to 2. This could be path B. And we could have taken a third path called path C, for example. Okay, it really depends on the gas and what you're using in terms of gas and how the system is going through this work. Okay, there's many different ways that the gas can expand. So we can say that each path will have a different area underneath. We agree that path A has a different area than path C. So each path will have a different area underneath. And what that means is we define work, since the area can be different for different paths, we can define work as a path function. Work is called a path function. It depends on the path. Okay, so work between 1 and 2 is not always the same. And what that is also called in mathematics is an inexact differential. So dW boundary is also called an inexact differential. Okay. So what about the volume? Let's look at the volume. Let's look at what volume and how volume works. So let's compare volume to work. So let's compare volume to work. So volume on the other side, if we look at the change in volume from 1 to 2, it's equal to volume 2 minus volume 1. Do we agree? The volume change between A, B, and C is always going to be the same. It's just going to be equal to delta V, or V2 minus V1. So the change in volume only depends on the initial and final state. So change in volume only depends on initial and final state. The work depends on how you get there and what you're doing, essentially. Okay, so it is a little bit different in the way that it is done. Okay, so we already know that there's two ways to solve for work, right? We know that one way is to have so two ways to solve. And I'll just rewrite it down so that we have it clear in our heads. Two ways to solve. One is to look for the area under the curve. Okay, so if we can solve the area under the curve, we can find work. The second way is using an analytical method. And that analytical method is going to use pressure is equal to a function of volume. Now, let's take an example. Let's look at a different example. Okay, so let's look at a very simple example of how we could find it area under the curve first. Okay, so for area under the curve, let's say we have a system, piston cylinder assembly again, and we have the system, and we know that the pressure outside is atmospheric. Okay, so the pressure acting on the system is atmospheric, and we know we have a gas inside our system. And now we're going to heat the gas. We're going to add heat to the gas. So what's going to happen is we're going to go from state 1, which is going to be this position right here, to a second state where the gas is going to start expanding. So state 2 is going to look something like this. Our piston is going to move up and is going to reach a higher point. And this is going to be called state 2. Okay, and we'll do some example problems, but we've already defined what a state is and how it works. So we have state 1, then state 2, because we expanded the gas by heating it. So what would this process look like on a PV diagram? So let's try and plot this process on a PV diagram. So if we plot this process on a PV diagram, we can say that 0 is here. We can also say that there's a certain volume of gas 1, sub 1 in this system, and there's a certain volume of gas sub 2 in this system. Okay, there's more volume in the first system than the second system. So we know that V1 is, for example, going to be somewhere here, and V2, our final volume, is going to be somewhere here. Now, what information do we know about the pressure? We know that pressure atmospheric is acting on the piston. Therefore, it means that the piston is free to move. So we know that the piston is free to move. And if the piston is free to move and the piston moves up, does it change the pressure inside our gas? No, it does not. The pressure stays constant. The pressure from the outside acting in is always atmospheric pressure. So we still have atmospheric pressure acting on this piston at all times, even though the inside expands. So that means that pressure 1 is equal to P atmosphere. The pressure inside of the gas is equal to the pressure outside. Okay, we're in equilibrium, so we have the same pressure inside as it outside. And same thing for P2. Pressure 2 is going to be the same as pressure 1 and is going to be the same as pressure atmospheric because we're just in equilibrium with our piston. Okay, so that means that from 1 to 2 we're going to have the same pressure, and this pressure is going to be P atmosphere. So we're going to start at point 1 and we're going to go to point 2. The pressure is always the same. So our process is going to look something like this. Now, what if we said let's do something different? Let's have a piston cylinder assembly and let's have our position 1 like this, and we're going to add stops to our system. So we're going to add little stops that are going to stop the piston from moving up. And now what we're going to do is we're going to heat it. So we're going to add heat to the gas. What's going to happen to the volume if we add heat? So this is volume 1. If we add heat to the system, we're just going to be trying to increase the volume, but the volume can't increase, right? We're blocked by the stops, so it's going to try and move up, but it's blocked by these stops right here. So the system is going to stay in the same position. Okay, so it's going to stay in the same position. Now, if we plot a PV diagram, we now know that point 1 and point 2 are going to be in the same position. So V1 is equal to V2, and it's going to be in this position right here. Now, how about the pressure? If we start adding heat to something, what happens to the pressure if we add more heat and we keep the same volume? The pressure is going to go up. So we're going to have a pressure 1 of atmospheric, for example, and then so this would be pressure 1, and then pressure 2 would be somewhere higher. So pressure 2 would go to here. So now we have a system that goes from 1 to 2. Now, what I would like you to do as an exercise is to try and figure out what the work boundary would be. So remember, work boundary is the area under the curve. So it's this area right here, the area between these two bounds. So work boundary is equal to the area under the curve. So we know that this pressure changes from P, the area is P atmosphere minus 0. So we can write the pressure difference is P atmosphere minus 0. Okay, we're just finding the area of a square. And the other component of the area, the length, on the V side is just V2 minus V1. Okay, and it's always 2 minus 1 because we always look at the final position minus initial. And so we get that our work boundary is just, in this case, P atmosphere times V2 minus V1. And this will become useful when we start doing example problems. Now, in the second system, do we have any area under the curve? No, we don't. It's a vertical line. There's no area. Therefore, the work boundary is equal to 0. And it makes sense. Whenever the piston does not move, we do not have work. Remember, work is force times distance. If there is no distance, there is no movement, and therefore there is no work. Okay, work has to be done on a system. Work has to be done by movement. Okay, so I want to go a little bit further into this and look at some further examples of how to find the area under the curve. So, but I'm going to go a little bit faster now because we've already gone through a few of them. So let's look at the system A, where we have a gas trapped inside a box. Okay, so the box does not move, the box cannot change shape, and the gas is trapped within the box. If we draw a PV diagram of this, we would have pressure going from one, and we add heat, so we're going to add heat to all of these. If we add heat, our pressure is going to go from 0.1 to 0.2, and our work is going to be equal to 0. Okay, very simple. And I'll put work boundary. Work B is equal to 0. That makes sense. There's nothing moving. The gas is trapped, and it's just going to increase in pressure. Now, in B, in example B, we're going to have the same type of system as before. We're going to have a system where we have a piston cylinder and we have some stops that are now placed higher than the piston itself. So the stops are placed higher. So what's going to happen in this case? So in this case, we're going to add some heat to the gas. And by adding heat to the gas, the piston is going to start moving up. Okay? It's going to start moving up until what point? Up until it reaches the stops. So once it reaches the stops, the piston is going to be stuck here. What's going to happen after it gets stuck there? The pressure is going to start increasing. So up until the piston has reached the gas, the pressure is going to be constant. After that, the pressure is going to start increasing by the fact that it's blocked by the stops. So if we were to draw this on a PV diagram, it would look something like this. And we'll do some examples in part 2, so do not worry if you're not completely following, but this is definitely helpful for theory. So we would have position 1 would start here, and then we would have a process that goes to 1B. Okay, we're going to call this 1B. And 1B would be as soon as the piston reaches the stops. Once we reach the stops, if we continue heating the system, we cannot move the piston anymore. So the pressure is going to go up. And this would be our final point 2. Okay, so we don't have a direct path from 1 to 2. Our path is from 1 to 1B up until we reach the stops. Pressure stays constant. And then as soon as we hit the stops, we now have no more movement and we start increasing the pressure. Now the work in this case is just the work under the curve. So it's just this part. So from 1b to 2, there is no work being done. So work is the same equation as the earlier example. Work boundary is equal to P1, whatever P1 is. Okay, it might be P atmospheric, usually it is, minus 0 multiplied by V2 minus V1. Okay, in our next example, we have another interesting problem. We have a problem where we now have a piston and it's connected to a spring. So it's added to a spring, and this is a special type of problem that you can memorize or you can have handy. And essentially, pressure is added from a spring, and this is called a linear spring. So we're only going to be studying linear springs. So if we have a linear spring, what is it going to look like on a PV diagram? Well, this is actually going to be a special case. So let's say this is position 1, and then we add some heat. So we're going to add some heat to this, and our piston is going to start moving up and resisting against the linear spring. So this special case, what happens is we start at a low volume in position 1, and because we're going against a spring, we now have more and more and more pressure as the volume increases as well, due to the fact that we're against a linear spring. So this is a special case where the final position could be somewhere here, somewhere higher, and this could be position 2. And so we would have a pressure 1 that would be lower than pressure 2, and volume 1 is lower than volume 2. Okay, but this is a special case with a spring. And how would you find the area under the curve? Well, you can just use very simple geometry. This is a straight line. So what we're going to have is we're going to have the area under this square plus the area under this triangle. So we're going to have this area added to this area right here. And we're just going to add them together. And the equation for this area is actually work boundary is equal to 1/2 P1 plus P2 multiplied by V2 minus V1. You can also do it with a triangle first and then the square. You'll come out to the same simplified equation. Okay, so we're going to look at one more example of area under the curve, and then we're going to take a break and go into part 2, where we're going to look at the analytical relationship and how we can develop some analytical studies of changing pressure and work boundary. Okay, so our last example is going to be concerning some compression and some cooling, essentially. So what we're going to have is we're going to have another piston cylinder assembly with some stops, and let me just redraw this so it looks a little bit better. So we have a piston cylinder assembly, and our piston is going to be at the top somewhere here, and we're going to have some stops at the bottom now. So our stops are going to be at the bottom somewhere, and what we're going to do is we're going to assume that this is already hot and it's cooling. Okay, so this would be position 1. And position 1 would start, and we would start having some cooling. What happens when we cool something? When we cool a gas? If we cool a gas, our piston is going to start moving down. So try to pause the video here and try to figure out how the PV diagram would look like if at the end our piston would be in this resting position here. So what it would look like is something like this. We would have a PV diagram like this with pressure and volume, and we would start at a high volume, volume 1. Okay, we always keep volume 1 and volume 2 where they are respectively. So volume 1 would be high, pressure 1 would be high as well, because we now have a hot gas and we're going to cool it down. And initially the pressure is just atmospheric pressure, right? We have atmospheric pressure this way, and so the pressure inside is also atmospheric pressure. So we're going to start with a movement from V1 to V2. V2 is where the stops are. So this is V2 here. Volume 2 is where below the stops we are. And so you're going to get to a point here, which is called point 1B. Okay, it's an intermediate point. And then once you reach that level, if the gas continues to cool, you're going to start seeing a lower pressure within the gas because the gas is resting on the stops. So you're going to start seeing the pressure go down in your system up until point 2, if that is the case, right? If the cooling continues. And it really depends on the case, but this would be the most complete case. And our work boundary in this case would be equal in exactly the same way as before, the same equation, P1 minus 0, okay? If you look at this, it's the area under the curve, so the area under the curve is right here. Okay, it's between these two values. The part from 1B to 2 doesn't matter at all for work. It just matters in the way that you draw the PV diagram. So it's P1 minus 0 multiplied by V2 minus V1. We always look at 2 minus 1. And this would actually turn out to be negative, because if you look, V2 is smaller than V1. So this term would be negative. Okay, the second term would be negative. Therefore, word boundary would equal a negative value. And that makes sense, because in this case, the work is done on the system. So the work done is not positive, it's not done by the system, it's done on the system. Okay, we're now compressing the system. Okay, so we're going to take a break now, and I'll see you all in part 2, where we will be discussing analytical ways of solving for the work boundary. So we looked at all the ways that we can find it in terms of our area and area under the curve. We looked at a bunch of different ways. Next, we're going to be looking at mathematical methods to do so when you have curves that are not simple to analyze, just like flat lines. Okay, so we'll see you in part 2.